I'm Caroline Simpkins, a former ballerina turned researcher, and today's episode is part 2 of 3 in a series on ballet and fall prevention, the central focus of my research. In last week's episode, we explored the importance of fall prevention and examined how specific aspects of ballet training may help reduce fall risk through improved balance, strength, and coordination. If you haven't had a chance to listen to that episode yet, I recommend pausing here and starting with part 1 to gain the full context and get the most out of this series. In today's episode, we'll delve into the pilot study I conducted with professional ballet dancers, where we investigated how they respond to unexpected balance disturbances, specifically standing slips. We'll discuss the methodology, what we learned, and how this study helped lay the groundwork for future research. Then in next week's final episode, I'll share details from my dissertation project, which focused on fall risk in older adult ballet dancers, bringing us full circle in understanding how ballet may be applied to fall prevention across the lifespan. As I mentioned previously, during my time as a PhD student, I worked in a biomechanics lab that focused on fall prevention across a range of populations, including healthy older adults and people with neurological conditions such as Parkinson's disease, multiple sclerosis, and Alzheimer's disease. Given my extensive background as both a professional ballet dancer and ballet instructor, I was particularly interested in exploring how ballet training might contribute to fall prevention efforts. With guidance from my PhD advisor, I designed a study that brought professional ballet dancers into our lab to examine how they responded to unexpected balance disturbances. Specifically, we used a specialized treadmill capable of simulating slips to evaluate their reactions. We then compared their responses to those of a control group, similarly aged young adults who were physically active doing other types of exercise and sport but had no formal ballet or dance training, and we referred to these people as non-dancers. At this point, you might be wondering, why study fall prevention in healthy young adults when it's older adults who are at greater risk of falling? That's an excellent question. This initial project I conducted with professional ballet dancers was what we refer to as a pilot study. A pilot study is a small-scale preliminary research project designed to assess the feasibility and practicality of a larger full-scale study. Think of it as a trial run that allows researchers to identify potential challenges, refine methodologies, and evaluate whether the research design is viable for broader application. In this case, before applying the slip perturbation protocol to older adults, we wanted to establish a foundation by first testing it with young, healthy people. This approach allowed us to explore initial outcomes in a lower risk population and to ensure the experimental setup, such as the slipping simulation, was safe, effective, and capable of generating meaningful data. Another key advantage of conducting a pilot study is that it helps determine the appropriate sample size for future research. This is critical for ensuring that a larger study has sufficient statistical power to detect real effects or differences between groups. So while our ultimate goal is to apply this work to older adult populations, starting with young adults was a necessary and strategic first step. This pilot study aimed to investigate whether professional ballet dancers exhibit different responses to slips during standing compared to non-dancers of the same age. Drawing on my experience as both a ballet dancer and instructor, I hypothesized that ballet dancers would demonstrate superior responses to slip perturbations, given that ballet training encompasses balance and muscular strength conditioning, key factors linked to reduced fall risk. Given the exploratory nature of this pilot study, a relatively small sample size was appropriate. So for this project, we recruited 20 young adults, 10 professional ballet dancers, and 10 non-dancers. When recruiting human participants for research, it is essential to establish clear inclusion and exclusion criteria to ensure that each group is as homogeneous or similar as possible. This homogeneity within groups allows for more valid comparisons between groups. For the professional ballet dancer group, inclusion criteria required participants to be currently employed by a professional ballet company and actively training in ballet, attending classes at least 4 days per week. And the non-dancer group included people with no prior dance training experience. Exclusion criteria applied to both groups and included any diagnosed musculoskeletal or neurological disorders, as well as recent major injuries, to avoid confounding factors that could affect balance and slip response. So, having defined our two distinct participant groups, the professional ballet dancers and the non-dancers, we proceeded with the experimental protocol in our biomechanics lab. Our lab is equipped with a 9-camera Vicon 3D motion capture system, which enables the collection of detailed motion data used to quantitatively analyze human movement, specifically in this study, responses to unexpected slips. The initial step involved placing reflective markers on multiple anatomical landmarks across each participant's body, including the arms, legs, trunk, and head. This process is analogous to the motion capture techniques commonly used in film and video game production, where people appear to be covered in small reflective spheres. The motion capture system tracked the 3-dimensional spatial coordinates of these markers throughout the trials, providing precise data that allowed for a comprehensive analysis of slip responses between the ballet dancers and the non-dancers. To induce slips safely, we utilized a specialized treadmill in our lab equipped with an overhead arch system to which a safety harness was securely attached. After fitting participants with the reflective markers, they put on the safety harness and stepped onto the treadmill to begin the slip simulations. The participants were given specific instructions. While standing still on the treadmill, they might experience a slip-like perturbation, but its occurrence and timing would be unpredictable. This approach was designed to closely mimic real-life scenarios where slips and falls are typically unexpected. Our protocol, therefore, aimed to replicate this element of unpredictability while ensuring standardized procedures and maintaining participant safety throughout the experiment. In this study, slip perturbations were induced from a standing position, meaning the treadmill belt was stationary at the start of each motion capture recording. During the slip simulation, the treadmill belt suddenly accelerated forward, causing participants to experience a backward loss of balance. To illustrate, consider standing on a stationary train or subway car that suddenly accelerates forward without warning. If unprepared, this unexpected movement can disrupt your balance, requiring rapid adjustments such as stepping with one or both legs to regain stability. The treadmill-induced slips in this study were designed to replicate this type of unexpected balance disturbance. For clarity, a trial in this study refers to a brief, approximately 10-second recording during which participants stood on the treadmill in preparation for a potential slip. At the start of each trial, participants were cued with a countdown, after which they remained stationary. During non-slip trials, participants stood still for the entire duration without any treadmill movement, though they anticipated a possible slip. In contrast, during the slip trials, the participants stood still for about 5 to 6 seconds before the treadmill belt abruptly accelerated, inducing a slip and causing a loss of balance. Each trial was conducted independently with a short rest period between trials to allow for participant reset. The trial sequence in this study consisted of 3 consecutive non-slip trials, followed by 5 consecutive slip trials, meaning each participant experienced a total of 5 sequential slip perturbations. Throughout the 5 slip trials, we collected detailed motion capture data with a particular emphasis on recovery steps, which are central to our analysis. Each trial began with the detection of slip onset, the precise moment when the slip perturbation was initiated. Following this, we focused on 2 key events that define the recovery step: liftoff and touchdown. Together, these events provide critical insight into how participants respond to unexpected balance disturbances and regain stability. Before presenting the results, it is important to clarify the concepts of reaction and adaptation, as these are fundamental to interpreting our findings. Each participant in this study experienced 5 discrete slip trials while standing on the treadmill, and our analysis focused on 2 key perspectives. First, the initial reaction to the very first slip, and second, the adaptation across the 5 sequential slips. The initial reaction provides valuable insight into how a person responds to an unexpected slip event, analogous to real-world scenarios such as sudden acceleration on a train or bus. Importantly, participants had no prior knowledge or anticipation of the slip during their first exposure, allowing us to assess their spontaneous, unprepared response. In contrast, adaptation refers to the changes in participants' slip responses observed from the first to the last trial. Adaptation can occur through improvements in proactive control, reactive control, or a combination of both. Proactive adjustments take place before the onset of the slip, while reactive adjustments occur in response to the slip itself. Referring back to those 3 events, onset, liftoff, and touchdown, the posture of a participant at slip onset when they are anticipating the slip provides insight into proactive control strategies. For example, after experiencing that initial slip, a person may lean their body slightly forward in following trials to better prepare for the perturbation. Conversely, the liftoff and touchdown phases, which occur after the slip onset, reveal information about reactive control. By the final slip trial, participants may have effectively learned through their central nervous system to initiate recovery steps more rapidly, thereby improving their slip recovery. This process reflects a trial and error mechanism governed by the brain and spinal cord, aimed at enhancing motor responses over time. Repeated exposure to slip perturbations, as implemented in this study, is a form of perturbation training that facilitates adaptive motor learning by engaging both neural and musculoskeletal systems. Turning to the results, we first examined participants' responses to the initial slip. Consistent with our hypothesis, the professional ballet dancers demonstrated superior recovery performance compared to the non-dancers. Specifically, the dancers had better stability at the completion of their recovery step, which again we called the touchdown. Additionally, the dancers took larger recovery steps, and they completed these steps at a faster speed than the non-dancers. Notable group differences were also observed in the trunk position and movement. Throughout the slip and recovery phases, including onset, liftoff, and touchdown, the dancers had more upright trunks than the non-dancers. Furthermore, at touchdown, the dancers' trunk backward velocity was slower than that of the non-dancers, suggesting enhanced trunk control. Collectively, these findings indicate that ballet dancers possess superior trunk stability and control during slip recovery from that first unexpected slip. Secondly, we examined adaptation in both groups across the sequence of slips from that first to the last trial. Overall, the results demonstrated that the ballet dancers adapted more effectively to repeated standing slips than the non-dancers within the same number of trials, which was 5 in this study. This superior adaptation among the dancers was primarily reflected in improved reactive balance control, as indicated by significantly reduced step latency and shorter slip distances over time. In contrast, both groups demonstrated comparable improvements in proactive balance control. These findings suggest that dancers exhibited a more efficient reactive but not proactive adaptation to successive slip perturbations, offering partial support for our hypothesis that ballet dancers would adapt more effectively to repeated standing slips than non-dancers. So what conclusions can we draw from these findings? The ability to respond to a perturbation with a rapid and effective recovery step is critical for preventing falls. With slipping simulations, these rapid steps always occur in the backward direction. The dancer's proficient execution of backward stepping is likely linked to their ballet training, as backward movement is a fundamental component in ballet. Consequently, long-term ballet training may enhance dancers' confidence and comfort in taking larger and quicker backward steps when recovering from a backward loss of balance. In contrast, non-dancers whose everyday locomotion predominantly involves forward stepping may have less experience with backward stepping, resulting in smaller and slower recovery steps that may be insufficient to restore balance, thereby increasing their risk of backward falls. Also, ballet dancers have lots of experience standing and balancing on one leg, a skill extensively practiced in ballet, which may contribute to their ability to execute longer and faster backward recovery steps more effectively and with greater ease than people without such training. Effective control of trunk movement was a key factor in the dancer's superior ability to restore balance following the initial slip perturbation. Limiting excessive backward trunk rotation during a slip is critical for fall prevention as it helps maintain stability. When slipping backward, strong core and trunk control allows a person to counteract the loss of balance by keeping their body weight and center mass positioned more forward, which is opposite the direction of the slip. In this study, the dancers consistently maintained a more upright trunk posture than the non-dancers across all three critical phases of that first slip response, the onset, liftoff, and touchdown. Furthermore, the dancers showed a slightly slower backward trunk rotation velocity at the completion of their recovery step following that first slip compared to the non-dancers. However, when examining adaptation from the first to the last slip, no significant differences were found in trunk variables for either group, indicating that trunk orientation did not play a notable role in adaptation to repeated slip perturbations. The enhanced trunk control observed during the initial unexpected slip may be attributed to ballet training, which emphasizes maintaining an upright posture with body weight centered primarily over the balls of the feet. This posture facilitates fluid movement, efficient changes in direction, and optimal alignment of the lower extremities. Additionally, the dancers may possess stronger core muscles due to the near constant core engagement required in ballet. However, confirming this hypothesis would require electromyography or EMG data of core muscle activity, and unfortunately, we did not collect such data in this study. One limitation of this study is that the ballet dancers had extensive training, on average 14 years, beginning at a young age between 5 and 10 years old. Prior research has demonstrated that dance education during pre-adolescence and adolescence significantly impacts motor development, including improvements in flexibility, coordination, agility, and dynamic balance. As a result, the ballet dancers in this study may respond to the standing slip perturbations differently than people who begin ballet training later on in life, such as in adulthood. Therefore, future research should also examine stability and balance recovery following slip perturbations in healthy and clinical adult populations who began their ballet training later in life. This study has some other limitations. First, all the participants were healthy young adults, so at the time of these publications, it remained unclear how ballet training influences stability and fall risk following a slip in older adults. Although I will address this in more detail in next week's episode, as my dissertation project specifically investigated this very topic. Second, the study was limited to only 5 standing slip trials per participant, leaving open the question of whether the findings would differ with a larger number of slips, such as 10 or 20 trials. Third, electromyography or EMG data from leg and trunk muscles were not collected, which limits our understanding of the neuromuscular mechanisms that underlie how dancers respond and adapt to slips, both proactively and reactively. And finally, this research focused exclusively on standing slips, so we cannot necessarily generalize our results to other types of perturbations, such as standing trips or slips and trips occurring during gait. And by the way, for clarification, slipping typically causes a backward loss of balance, like we've discussed today, while tripping usually results in forward loss of balance, such as stumbling over an obstacle while you're walking. So to conclude, this study was the first to investigate the responses of professional ballet dancers to 5 slip perturbations, providing preliminary evidence that ballet training may reduce the risk of slip-induced backward balance loss. Although this pilot study focused on healthy young adults, the findings align with prior research demonstrating the benefits of ballet-based interventions in enhancing balance and functional mobility, particularly in older populations. Overall, professional ballet dancers were more stable than the non-dancers when exposed to that first unexpected standing slip. This better stability likely reflects enhanced resilience to backward balance loss, supported by more effective recovery stepping and superior trunk control. Additionally, the results suggest that ballet training may facilitate more efficient adaptation to repeated perturbations, potentially improving resistance to balance loss and decreasing fall risk in young adults. Taken together, these findings provide early support for the potential use of ballet training as a targeted strategy to enhance balance control and mitigate fall risk, particularly in populations vulnerable to balance impairments. The data discussed in today's episode are published in peer-reviewed scientific journals. I will include full citations and links to these publications in the show notes for those interested in exploring the research further. I would also like to take this opportunity to sincerely thank my co-authors for their invaluable contributions to this research project, as well as the 20 people who generously volunteered to participate in this pilot study. If you happen to be listening, thank you again. In next week's episode, we will build on the findings from this pilot study by exploring how they apply to older adult ballet dancers, a project that formed the foundation of my dissertation research. The encouraging results from this pilot study on young professional ballet dancers provided strong justification for extending this line of inquiry to an older population. During my time as a ballet instructor, one of my most rewarding experiences was teaching ballet to adults, many of whom were older. While I observed firsthand the positive impact of ballet training on their balance, strength, and overall mobility, I recognize the importance of validating these benefits through scientific research. This motivation led directly to this study I will share in the next episode. Thank you for joining me today for the Ballet Science Podcast. Whether you are a dancer, teacher, student, or simply curious about the mechanics behind movement, I appreciate you being here today. Each week, we will explore the intersection of science and ballet, from injury prevention and biomechanics to nutrition, mindset, and everything in between. If you enjoyed this episode, please follow this podcast, leave a review, and share it with your friends and dance community. You can also follow Ballet Science on social media and visit our website, ballet.science, for additional information. Thank you again for tuning in, and I look forward to seeing you next time on the Ballet Science Podcast.